Okay, this lecture is the one that begins the core algebra of the Lagrangian, Hamiltonian stuff. And today it's the Lagrangian we'll take on. But it also begins a discussion of generalized curvilinear coordinates. You've probably noticed a lot of equations on the wall over there, and that's mostly about that differential geometry of coordinates that aren't orthogonal. So we're going to introduce that today. And remember, it's still the review section, but this is, as progressive education supposedly marches onward, we do things earlier and earlier in an undergraduate class. And just out of curiosity, how many people have studied generalized curvilinear coordinates in a math class, or else maybe you took a relativity class that had it? Okay, well, so I'm going to do it twice. It's a very important thing because you can use it all kinds of different things besides mechanics. But today we're going to use it just for particle mechanics, and we're going to derive the Lagrange's equations using that. So these are the steps. We're going to use the quadratic form for kinetic energy. We essentially derived Newton 2 in vector form. So there's just some Lagrange trickery we have to go through, and then we'll use the stuff to study, well, the thing that we didn't do so well before, and that was the Coriolis and other circular forces or accelerations. So a little bit of review here, just to remind you that we have these really three choices, but we're focusing on two of them, Hamiltonian and Lagrangian. And in this case, there was no spatial dependence of the options, only the momentum dependence of the Hamiltonian, which was equal to velocity. The derivative was the velocity, and the p gradient of h was v, and the v gradient of L was p. Those were our first equations for both Lagrange and Hamilton. This lecture is devoted to getting the second equation, but getting the first another way. So we're doing a complete re-derivation of that. Then Thursday we have the Hamiltonian to tackle as well. So at that time we'll be able to compare the two as well as derive one of them. Now just recall that as is shown on a very extreme right-hand side there and in the center slide, that there is a geometrical significance for these two equations. It involves tangents and sharing or duality sharing between the Lagrangian and the Hamiltonian. Lagrangian in blue, Hamiltonian in orange or reddish colors there. Same color scheme up here. So what we're going to do, as I said today, is go one step beyond this, and that is the second equations that right now are zero because there is no coordinate dependency here. But when you do have a coordinate dependency, then there's a beautiful symmetry between the Lagrange equations and the Hamilton's equation, except it's an anti-symmetry. We'll see that in the next lecture. Okay, now the polar coordinates is the first curvilinear coordinates that you're all should be familiar with. This is 2D polar coordinates. I'm going to give you a problem for 3 to derive all of the funny stuff that we need, but these are really OCC. This particular choice is orthogonal, and but we're going to go ahead and just use the more powerful mathematics of the generalized coordinates to well, speed the process here, as it were. Now, the chain rules that we talked about before, this is going back to lecture 8, and we're now considering how coordinate transformations can be expressed in a general way, or at least the beginning of that. So we have two variable functions here, and we have a pair of them, f whose chain rule is that with respect to Cartesian coordinates x and y. And then you have another coordinate g. F and g are going to be basically the functions that are associated with r, radius, and theta, polar angle. But start with just the first order differential form for the two is being written or will be derived here. Now the trouble is that if you were to start this way, which is a reasonable thing to do because you know the Cartesian coordinates and you're trying to inquire about differential effects for radius and angle, that's a bit of annoyance because right away do you happen to know the partial derivatives of an arctangent. I'm talking about arctangent 2 here. That's the theta. And this isn't too neat here either. It's the square root of x squared plus y squared. So you start right off on a bad foot because you waste your time doing derivatives of those complicated functions. But the thing to remember always about coordinate relations, the algebra of them, that it's really easy to invert the differential chain relations because they're linear, you see, even if the functions are not so easily inverted. In other words, if the inversions of your functions are complicated, well, just go and use whichever is less complicated. In this case, the expression of x and y in terms of r and theta is very, very elementary. So start with that one, okay? And make a chain rule for that one involving the curvilinear, or GCC in general. This is OCC, okay, orthogonal curvilinear coordinates. So what I'm doing here is just going ahead and writing out a matrix relation using a matrix that's called the Jacobian. So this is the Jacobian for these two r and theta in terms of Cartesian coordinates, that is the derivatives of the Cartesian coordinates, okay, which are very easy to calculate. And that is a lot quicker than screwing up and messing with the derivatives of those things. So that's the deal here. Now you'll notice that if r was equal to 1, if you write on a unit circle, this is a rotation matrix. That's kind of neat. Okay, that's something that you would notice and then maybe use for something later. Right now I'm not going to dwell on that, but you should notice that in any case. Okay, so what we're in general going to have, and this is the notation that we'll use. I won't always draw the curvilinear coordinates in a mauve color, but I should say a word about why every piece of literature that deals with these, and it's mostly relativity literature, the Q's are what we use as letter. In other words, what does the Q stand for? And the best thing I can come up with is Q stands for queer, okay? Now, they do get pretty queer. We're going to see that in lots of examples. We've already seen it, actually. Those overlapping ellipses that we got when we did the phasor stuff. That's pretty queer for a coordinate system. Okay. Anyway, remember when you see a piece of literature, Q is what you get to use as the variable. This goes back to, I think, Gauss, but then it's a little weird. In any case, there's something else that's going on here that we've got to get used to, is the Q's have upper indices. And we're going to be very particular about having indices that are up and then indices that are down. One's going to be called contravariant when the indices where you usually put it, that is down, is called covariant. Now we'll go into those terminologies and make some anthropomorphic mnemonics to help you with that. But for now, the thing that I want to make sure you see is something called the dummy index rule. This is shorthand way of writing something with a sigma in it. You're going to be summing over several of these at a time, so you don't want to have to be writing sigma blah 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 and then another sigma blah 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 for each pair of indices that, or maybe more than a pair of indices that are being summed. So the rule is, if two indices appear the same letter, same symbol on one side of the equation, you sum over them. If they appear on both sides of the equation, not necessarily sum, okay? That's basically the dummy index rule, all right? And then these guys right here are plain, quote unquote, Cartesian coordinates. And, well, for relativity, special relativity anyway, there are 4 of those, and we let time be one of them. We're not going to do that right away. That's going to come much later in this course, really toward the end. But that's the main thing that may not be something you're used to and should get used to as quickly as possible. Okay. Now, when you actually write these equations and they get complicated, it really helps to, if you have a pair that are being summed over, just drop a line between them. It's easy to do with a pencil, right? It's not so easy to do if you're writing a paper, so nobody does it in the literature. They figure that you're grown up and you can see the two indices even if they're separated by 150 characters, okay? That's sometimes what happens. Okay, so let's take a look at those equations in general while using an example. Okay, and the idea is that we have both the first differential and then the first derivative with respect to time in particular. So when it comes to generalizing coordinates to generalized velocity, okay, in this case it's the Cartesian coordinate velocity, x jth component, and now we're being strict. We're saying I'm going to write my components in a professional way with the coordinates up in the air, contra variant. I kind of remember the Iran Cartras. You're probably showing my age, but they're revolutionaries holding a knife up, right? Contra. Okay, so that's why you remember contra has a knife up in the air. Anyway, here's x dot j and dx contra index j. Okay, both of them have the same partial derivative here. All we did was divide by dt to make this dot thing. Okay, so that's a lemma we need for Lagrange derivation trickery later on. This is what we're going to call lemma 1. Color it in red, really important. That is the Jacobian that goes with the generalized velocity and the Cartesian velocity, or in general, the Cartesian, the generalized queer coordinate velocity, and maybe another different queer coordinate system. Okay, that with a dot on it. And this doesn't work when you're doing relativity, but it works for most of the mechanics that we do at low speeds. That's the same as the Jacobian you have for the coordinates. Okay, that's lemma 1. Okay, and I want to make sure that you see the why of each of these lemmas that we're setting up mechanics with. Okay? Now I'm going to try to keep up at least one of these screens with what we're doing here. So the next stop here will be this little thing right here, where we already mentioned the coordinate transformation between r theta and x and y, at least going in one direction. We're going to have to go in more than one direction very shortly here. So that's just in one direction. The thing that was almost a rotation matrix, right? Okay? So this is our definition for the Jacobian, and it applies, according to lemma 1, to both the velocities, the dotted variables, and the original coordinates. Now this is kind of a joke, and it isn't my joke. I think somebody else thought this up, but there are books that call the inverse of this matrix the Kajobi. Okay, so we use letter K for it. Okay, and of course, with 2 by 2 matrix, really easy to do an inverse. I mean, basically all you do is put a minus sign on the off-diagonal components and flip the diagonal ones, right? Oh, and don't forget to divide by the determinant. If you don't put the determinant in, you have a matrix that's called the adjunct. Okay, is that terminology more or less familiar? Okay. In any case, always test your inverse matrices if you're taking a test, okay? Avoid mistakes. If you're preparing for a paper to present somewhere, you check them twice. Okay? There's lots of mistakes you could make that are very subtle that involve not checking your inverses. In any case, we've got this matrix right here, and so what we need to do to get it is go ahead and stick the determinant down here. Now the determinant is very easy to see. Instead of being a nice 1 that it would have been for a rotation, it's got an R that's been added to one column. So the determinant of J is R. That's sitting in the denominator. So you end up, well, after you've done the operations of flipping here, this guy down to here, and then taking the R off of one and putting it inversely on the other. And then I see the minus sign here is barely visible, okay, but it is there. And that is the inverse that we're talking about. So what you have to do right away after you make this thing is check that when you multiply this by this, you get the unit matrix. Okay, so that's really all I want to say about that, I think. But the deal is that this is going to always be true for any number of dimensions. So basically what you're going to have is you're going to have the Jacobian. Okay, remember we defined the Jacobian as the partial derivative of the Cartesian guys with respect to the Q guys, and then the inverse turns out to be the Q with respect to the original Cartesians. Okay, so K is here, that's this guy, and here's J, either way. And then what you've got is a chain rule over the Cartesian coordinates. So you end up here, and this is just trickery, mathematics should spend a day on this, probably proving it, but the partial of Qm with respect to Qn, the idea is these are independent variables. So this is usually 0, only when they're equal, and then of course the partial variable with respect itself, 1. So this is the proof that these are inverses of each other. The kind that a hand-waving physicist does, right? Okay. And that's what's going on right there. All right, those are pretty important ideas. They're very simple, though. This one, not so simple. This one's a little weird. Lemma 2. That we need to do Lagrange's trickery. This is generalized acceleration coming here. Okay, generalized velocity, pretty easy, lemma 1. But generalized acceleration, a little more complicated. Because these are curved coordinates. You've got to do something to indicate that your coordinates are going around the corner. So you're going to have really 2 derivatives that come out of this thing. If I take x dot j and write it with a nice Jacobian here in terms of q dot m, a sum, of course, this is a sum. This is not a sum, although you could sum the whole equation, but you don't. You just do what's on one side of the equation, and then you look at that and you say, hey, I got to take a time derivative, not just of this guy. In other words, I can't just write the Jacobian times q dot dot, and if let's say I'm done, this guy is going to, in general, be a function of time. So you're going to have a total derivative here that you take of the Jacobian matrix components. All of them involved in that sum, well, the m being from, in our case, r equal phi, or m equal r, and m equal the theta angle that we're using for pole. Okay? So that's what makes this complicated. Okay? So we got to do a little bit of thinking here about how this is. If I apply the chain sum to this Jacobian, okay, That is, I say to it, okay, this thing's a function of coordinates, so I'm going to take a partial derivative with respect to the coordinates. That means I have to sum over this thing times dqn dt. Okay? And this thing right here has to have that done to it. So I have a double partial derivative here with respect to qn, but qm has been taken first. And then there's this a velocity, generalized velocity, associated with that. Okay? But remember, these guys commute if this is a continuous differentiable function, right? So I can turn those m's and n's around. I can put the m on the front and the n in the back, okay, and leave me with a partial of qm of this thing, okay, right there. That partial x with respect to qn, then dqn. Well, what is that? That's just the velocity, x dot. Oh, and the partial of qm of it. That's lemma 2. Okay, so here are the two. First of all, the one we just derived, which is lemma 2, okay, for setting up Lagrangian stuff. And it's the total time derivative of the Jacobian is just a partial derivative of velocity with respect to q itself, a coordinate. So it's a weird thing, velocity and a coordinate in a partial derivative. And the other one that we just got done with, and that's this thing right here, the actual Jacobian is the velocity Jacobian. That's what we got there. So velocity easy, acceleration a little bit more difficult. All making sense? Okay. All right, let's do it. This is how to say Newton's F equal ma in the worst kind of coordinates that you can possibly have. All right? We're used to saying it in Cartesian, now we're going for the big time. All right, and we're going to involve this guy and the F equal ma as well as the work relation, a definition anyway. Okay? So I say that we start with stuff we know, and I put in parentheses, sort of, because there's lots of whereases and wherefores and so forths that have to be really said. But anyway, writing out your quadratic form in terms of velocities is pretty easy. But there is one thing that I'm going to require here, and it is kind of a restriction that looks like it's killing this thing for being able to do any relativity. And to be truthful, it is. We have to do a little bit more to get to that stage. But here we're going to demand that these inertial things for a Cartesian position of a particle, or a system of particles, say 2 particles, each of them in 3 dimensions. That's 6 dimensions we're going to be summing over maybe. But whatever that is, since it's Cartesian, I want these to be constants. Otherwise, Lagrange isn't going to work for us. This is an important point that isn't usually made. So I want to state that right away. And this is going with this relation as well, the F equal ma relation. So this acceleration, that is x dot dot, summed over a mass tensor, that these guys have to be constants. Okay. Now that's going to make for trouble when you start doing the electrons in bands where the velocity is weird, right? So be aware of that. That's why you have to do some more work in order to get this Lagrangian stuff to work in a quantum mechanical situation. We'll attempt to do that before we're finished the review, but still I'm warning. Now this multidimensional version of the work energy differential is really key here. We're just setting it up. We're not going to do much with it except throw away all but one set of terms from it. But this is nevertheless the idea here. And the idea is that when I do force dx, and dx is here your first differential in the q coordinates, and I'm going to do my mass times acceleration sum here. So this is where we bring in these queer q's to make an equation that just involves them and get rid of the Cartesians altogether, if possible. Now, what we are demanding of the Q's is that they are independent. So this equation is true term by term. Each term is an equality. So I can just stop the sum altogether and just pick an m, okay, and write it. That the sum isn't necessarily there. What I mean is it still holds if all of the dq's that you have set up for this particular experiment or whatever are 0 but 1, and that 1 we're just going to make it a delta q equal to 1 and forget about it. So that's the first real trick of the Lagrangian development right there, is to assume these things are independent, and therefore I can write an equation involving each one of them in turn. So that m is not being summed, it's been picked out, one of the m's and then another one and another one, however many dimensions you have. And that's another issue we have to cover, and that will not be covered in this review unit. Here we're already set up with a curvilinear coordinate system that has 2 dimensions, and we're matching it with Cartesian x and y, which is 2 dimensions. Our first thing with the trebuchet, that'll be our first real mechanics problem. Doesn't look like that at first. You got to do some work. You get them matched. Okay, but anyway, there we are with a f equal ma equation, sort of. It's got all these partials and things like that sitting in it. So this is the generalized curvilinear coordinate force component f sub m. Okay, and the m goes with the q coordinates. We're almost out of the woods, except that we've got these x's here. I also got that one really is kind of bothersome because it's sort of Cartesian also. So we're not done yet. This is just the setup. Okay, now I said we'd keep up with things here, so I'm going to go over here and get to this point. There are the lemmas. There's the differentials it's going to have. There's the independence at work. There's the generalized force component. Okay. So the trickery begins, the real trickery that gives the Lagrange force equations. Okay. Now, trickery, it's obvious stuff. Okay, totally obvious stuff. If you've looked at it for a century or so. Now, we've got to be pretty careful with this. Okay? But basically the idea is that I've got something here that I would like to say is a double total derivative of something called A. Okay, so that is the double derivative, double time derivative. Dots always indicate time derivative of, there's the thing there is A dot dot. And then this little partial derivative here is B. Okay? And we know, just from our simple calculus, that a double dot B is a derivative with respect to time of A dot times B, A time derivative multiplied by B, minus thing with dots on both of the factors. Okay, that's what we're using here. Okay, so we're replacing this right here, okay, with this. Okay, so this is a single derivative of A dot. There's the A dot. Now remember, this would not work if m is a function of coordinates, right? So Lagrange is done. It can't do any further if that's the case. You got to do something else. All right? But we don't have that situation. These are constants. Okay, so we can do that. And it's also true for the one that has 2 time derivatives there. This is the time derivative of the x right here. That's A dot. Then here's the time derivative of a Jacobian, the B. Okay? That's this guy. All right? Well, we're almost there, except for one more piece of trickery. Okay? So, don't forget that is part of the story. Okay? And I say in very small print here that you can't read bye-bye relativistic mechanics or quantum mechanical dynamics. Okay. Got to do something else for that. As I say, we're going to attempt to do that later on. Okay. Now, first thing to do here is sort of match the second one. What I want to do is replace the partial x dot, and I'm going to use lemma 1 to do that. Okay, remember partial x with respect to q is, put both dots, you've got the same thing. Velocity Jacobian is the coordinate Jacobian. Okay, and then we've got this thing, right, that involves mx dot. Okay, and then this one right here is a derivative of a Jacobian, but we know that's nothing but a funny kind of Jacobian. Uses the velocity in the numerator and the queer coordinates, the Cartesian velocity in the numerator and the queer coordinate, without a time derivative in the denominator. Okay, so that's the second term being worked on. She also has a thing that looks like that. Okay. All right, now once again we use the product derivative relationship, except this one is being used where in this thing the q might be q dot, that's what it is right for this one, okay, or the q might be the actual qm, okay, and that's what we're dealing with there. Okay. So what we're doing is we have equations of the form mij of velocity, that's this one and this one, multiplied by this partial derivative with respect to a q that can be either this, that's this one, or this, that's that one. Okay? Bingo. That's Lagrange's equations right there. This is your kinetic energy. Summed over all the dimensions of whatever it is that's got Cartesian-like motion. Okay? Here's where the Cartesian coordinates disappear. Just call them T. That's what they use in most of the literature. This thing is called T, big T. Okay? Sorry, it's not a very good choice. Can't think of anything to say about it, but that's what it is. All right? And that's our equation right there. This is Lagrange, what I call Lagrange's generalized curvilinear coordinates. It's going to be true, you name it. Whatever queer coordinates you take, it doesn't matter how queer they are, this has got to work. They can even be moving coordinates, it turns out. I call this the four-wheel drive garbage truck of physics. It'll drive anywhere and take a load of crap. You can have some really crappy coordinates and it'll still work for you. Okay? The catch is that we still have a Cartesian F, and we'd like to get rid of that. So in order to get Lagrange's, French, okay? How do I look like a meme? Okay?
Kerchief.
To make this really French, I've got to get rid of that. They don't deal with garbage trucks in Paris. Okay, they deal with garbage strikes, but they don't deal with the trucks that much. Okay, so here's where we get Lagrange 1 and 2, as we say. Okay, it's still another trick up the sleeve, so to speak, but you already know this one. It's the physicist's gradient. The F equal minus the gradient. That is, the Cartesian F sub m is equal to partial u with respect to qm. That's what it's going to do. So you're saying right now, I want to get that fm in terms of the coordinates, the generalized q coordinates. So I write this. Okay? And then I say, I already got one of these. If I could just get one of these, or have it be 0, I'd be in business. Okay, that's what is the key thing going on here. Okay, so what we do is we define the Lagrangian to be the kinetic energy that we did for all the Super Bowl stuff, right? But we didn't have any potential that the balls were in. So here's where we put it in. Because if I put t minus u, the minus for that shows up very nicely in this, and you get 0 here. That's kind of cool. But this trick requires that this thing called the potential has no explicit velocity dependence. In other words, I definitely want the time derivative of this thing not to matter, to be 0. I've got to get rid of any velocity dependence for this thing, okay? So I don't want to have a partial derivative of a u with respect to q dot. That has to be 0. This thing has to be 0. That's the way we'll make this term not be hurt by defining L in this fashion. And once we've done that, then we get some really beautiful relations. These are the way I like to write these equations. This is what you usually see in the textbooks. But this is what we're really dealing with here. The momentum, this is our first equation, P sub m, and m is covariant. You see, when you have a contra in the denominator, then the result of the expression is a covariant quantity. So this momentum is covariant instead of contra like the coordinates. That's weird. That's just something that I think should come at the beginning of this discussion, and that's where I'm putting it as early as possible in the review section. But here is this equation, and then if that's the momentum, this is the time derivative of the momentum, this is p dot. You see, the total time derivative of momentum, p dot m, is simply equal to partial L with respect to qm, and there's some dirt or something in the screen that's making that up. But other than that, look at what you've got. One equation has the dot on the q, the other one's exactly the same, except you move the dot off the q and put it on the p. What could be easier to remember? All right? So that's the second GC equation. And you can see right away, and I think I've gone ahead and said this, if L has no explicit coordinate dependence, like our superballs, right? There's only velocity dependence, right? If it has no explicit coordinate dependence, then this thing, and if just one of them has it, then that particular momentum, m, has no time derivative, no total time derivative. It is a constant. It is a conserved quantity. It is a symmetry. That's a really fine way to say it, which we'll make more fuss about later on. Okay? So I think this, you see, is a really neat thing that's come out of just doing this first clever little trick of product derivatives in the formulas. Okay, well, let's take a look and see how this works out. We've got plenty of time to do this, so I can stop and answer questions.
Just one question on the previous slide, where we say that U are sort of like potential energy is so it does not have any velocity dependence, right? So if let's say it has a velocity dependence, and then the equation up there, instead of 0, we'll have a du over dq dot.
Like electromagnetism, right? Where you have a vector potential, right?
So, yeah, so my question was like that. So when we introduce this, are we saying that like the frame of reference is, instead of being non-inertial, it becomes inertial, and then by going from one space to
the inertial part of this thing is that M matrix, right? And that M matrix has already been subsummed into this, right? This doesn't have that. And this isn't going to get us very far in relativity because of that. I mean, the idea is that in relativity, things that you didn't think were related suddenly get all mixed up, like space and time, but it's also other things. There is a way for us to handle this. We can get our Lagrangian, and we'll do that when we talk about the electromagnetic Lagrange equations. Then you need vector potential and scalar potential. So what you're doing is getting closer to relativity. You're finding, okay, electromagnetism is a relativistic effect. We're not doing that here, for sure. Okay. So remember, for all of the things. Now, the whole idea of having a potential is kind of interesting and for an experiment, I might as well do this. I wasn't planning to do this, but I don't know if you could swing around to our little guy here, that where the balls that are the ball bearings are sitting in a trough and can do Super Bowl-like things, right? Remember? We kind of did that before. I don't know if I want to add this guy right away. There's something wrong with this one, and we'll see in a minute. But if I go here, even with just 3, I can have that effect of, most of the kinetic energy, not all because it's rolling, okay, but most of the kinetic energy goes out of the one and into the other, and it kind of works even if you have, 4 of them involved. Not bad, right? But it gets weird when you have this one. Pretty weird, huh? That had a potential. That's got a neodymium YAG, or one of the neodymium magnets. In fact, it's so powerful that I have to, like a mathematician, I'm trying to hold it back. Okay, it's really boom. Okay, so there is a potential, and it's a weird one, right? Because this is like a dipole. It doesn't kind of matter that much because this one just matches it dipole for dipole, right? And so you can write this thing as just as a function of simple linear distance. Okay? All right, you play with that thing after. I'll keep this one separate, the hot one, and you can play with that just to see it. Whoop! They found a metal ruler there, and we'll have to tear it away from that when we get to play with it. Okay, so that's kind of fun, right? That's, adding a potential, right? Well, actually subtracting it. That's kind of weird, isn't it? It's subtracting. We have to subtract it into Lagrangian. Lagrangian's weird, really weird. Okay, it is a quantum relativistic effect. Okay. Well, let's get just back to Earth here, so to speak, and just do in some detail the algebra, the vector algebra that goes with the Jacobian and a Jacobian. Now we got the Jacobian, okay, and remember we're talking about Cartesian coordinates x1, x super 1. You got to put a super on the coordinates, okay. They're contraries, okay. They hold lines up in the air. You got to put that x1, that's x, just plain x, and then x2, that's just plain y. So these two get partial y. And then q1 and q2, those two coordinates we've already decided are radius here and here. And then angle, in this case we're using angle phi, that's q2 here and here, okay? And then the inverse of this thing, remember how you get that, okay, you just minus these guys and flip these guys. Well, they don't do much in flipping except that the r comes up. We already have a 1 over r that we have to put in, so it gets taken off of that and put on this one, and ditto for those two. So there are our two matrices written out in all their glory. But what I want to point out is, once you've done this correctly, and that means check the inverse, okay? Once you've done this correctly, the columns of this matrix are called the covariant unitary, and unitary doesn't mean quantum mechanical unitary. That's a misnomer in modern physics, okay? But anyway, E sub r and sub phi, all of their generalized coordinates are downstairs, so the covariant puts its index downstairs. And that's this column right here is E sub 2, that's these two components, and then these two components are of this, okay? And then there's another set of vectors that are called the contravariant vectors. They're lines up in the air, okay? E super 1 and E super 2, E super R, E super phi is this row of the Kajobi. Now what you're doing here, mathematically, is something that you should also do when you take a quantum mechanics course, where you make the bras and the kets. Those are the ket is more like the covariant, and then the bras are like the contra, but it could be the other way. The idea is you have a dual coordinate system that will be orthogonal, actually orthonormal. You force the orthonormality by doing this. That's the key thing that's going on here. Now, with polar coordinates, it's no big deal. They're already orthonormal. But their dependency is quite different. You can see that these guys right here get bigger as we go out to bigger and bigger Cartesian coordinates, bigger and bigger radii, okay? Whereas these guys get smaller as you go out, okay? They're doing that so they maintain their scalar products. Their scalar products are invariant if you put the two of them together. And that's what you always do in quantum mechanics. You put a bra with a ket if you're going to do a scalar product. If you put a ket with a ket like this, you're making a two-stage system entanglement if you have sums of them. Okay? If you put them knuckle to knuckle, you're making an operator, right? Similar things happen here. Okay? So let's go ahead and just do a sketch. And these are 2D sketches. They look like they're 3D perspective. I don't want that to be the case. These are actual curves in the plane. Everything's in the plane here. The vector is in the plane. Okay? So, what is the covariant derivative of E sub 1? That's E with respect to R. Okay? Well, what we're saying about that E sub R, okay, this vector here, partial derivative of a of the Jacobian, what we're saying is that this character right here, that's partial derivative of R with respect to Q super 1. And then this is partial derivative of the vector R, radius vector R, as this guy right here, without the differential, with respect to the second queer coordinate. Now, here is, I'm just saying, we set this up, this curve right here is Q1 equal 100. And then up the line here is 1 unit distance in this queer space. Q1 equal 101 is right here. Meanwhile, the other coordinate, whatever that is, Q2 equal 200, and here's 201. So I've just made each one of these differentials here equal to 1. So what you get out of that is the sum of the number 1 covariant vector plus the number 2 covariant vector. And the idea is, if this is, not too big a differential, that we will have just outlined very closely a unit cell. But remember what the deal is that the partial derivative of the R, that's the R that's being traced by this thing, with respect to the coordinate 1, we're only varying coordinate 1. We're keeping Q2 equal to a constant with a partial derivative, right? So they line up. Quite the opposite of the supers. The supers are written as a partial derivative of R with respect to the Q's. Now I'm getting a little bit ahead of myself here, and that's where I really need two screens to go back and forth. Let's go ahead and look at the covariant ones over there on that screen, and then we'll look at the contravariant ones, which are down here. But the basic thing I want to get across here is that E1 follows the tangent. So this blue stuff is sometimes called the tangent space in all kinds of different applications of this. Okay? It has to follow the tangent because that's what it is, partial respect to Q1. It means Q2 cannot change. You see, well, it does because this is more than just a dr, it's a delta r. It's macroscopic, it's not infinitesimal. Okay. But you see what's going here is we're matching the cell walls, the unit cell walls, for this particular Q system. That one, that's what I mean by unit. When the Q's vary by unit. Now what unit are you going to pick? Microns? Be my guest. Nanometers? You'll get a gram. Just say nano, right? Okay, so that's the deal for a vector being written as a linear combination of partial r's with respect to the coordinates. Okay, a nice first linear, rank 1 linear differential. Okay, next stop, these guys. Okay, these guys, instead of being partial of r with respect to q, are partial of q with respect to r, which you know as the gradient. So now here's the coordinate with its knife up in the air, so these guys are going to have their knives up in the air. Contra. There's E2 and there's E1, and boy, they're a lot different from these guys, right? In this case, because I've got a non-orthogonal coordinate system for sure here. Unlike the polar coordinate system. Okay. Now, what happens here, and that's the thing that really makes this work, and first of all, there's the polar thing that we're going to be using this for. Okay, so here are those two situations with the gradient now being used, and of course that means it has to be perpendicular to that curve at the point that we're evaluating. Okay? And then this one right here has to be perpendicular to Q2. Now it's kind of in the direction, you see, what's kind of weird here is this guy's kind of looking like it wants to be something associated with Q1. It's not. It's reading off of Q2. And this one right here, this is the one that's associated with Q1. The variation of Q1 would be right on top of this as the orthogonal. Okay, so the normal space, tangent space, big distinction. Now, basically it boils down to, this is the physics sort of this, is these guys are usually used for extensive quantities. Things like distance, how much space you're taking up, or even velocity very much. But intensive quantities, force, momentum, things that are all sort of defined physically at a point. They would be often more convenient, but there's no rules about that. That's just a tendency that I noticed in using of these things. But this is the key thing. When I said that we force the orthogonality, this is what I mean. So put this on both screens so that it really stands out. Here we go with partial r with respect to qm, partial qn with respect to r. Well, that means I pick a coordinate, any one of them, and take them in turn. And that means I'm getting the partial of qn with respect to qm. If they're independent functions, that is 0 if n is not equal to m. But of course, if it's the same variable, n is equal to m, and you do write your delta function this way. Contra covariant. When you write them two together, that means something else. It's called a metric. Usually has a G symbol put on it. But I want to, not let you get confused by that. Okay? So, we kind of have here that thing that we talked about on this third screen there, covariant, then invariant. That's kind of like the Estrangian situation, okay? And then contravariant. So this is going to be the thing that Lagrange kind of uses more than anything else, and this is the one that Hamilton's going to kind of use more than anything else. But we're getting a little ahead of ourselves to say that. You have to see both of those, and we won't do the Hamiltonian until the next lecture on Thursday. But in any case, with our polar coordinate examples, here they are again. We've got the contras as the row of the Kajobian, which is the inverse of the Jacobian, and then the Jacobian itself has columns that make up the covariant vectors. That is, define the covariant vectors. So you see what you do in a mechanics problem is the first thing you do is get the Jacobian or the Kajobian, whichever is more convenient. And then whatever that is, you take the inverse of that to get the other one, right? Then you have those vectors, and those vectors are going to play the role of all kinds of things. And you have ways to check them as you go, okay? So here's the covariant metric coefficient. That's what this is. When you take the dot product of a co with a co, you get GMN. Now, if you really want to be nasty, you call that delta MN, but then you get in trouble because most people would say, hey, that's 1 and 0. This one is not. This one is 1 and r squared. Happens to be orthogonal coordinates, so no numbers here. So that's what we don't have yet, is a non-orthogonal situation. This is an orthogonal curvilinear coordinate system. And unfortunately, most math physics books, they just deal with OCC. They figure it's too much for people to go to the GCC. And that's a terrible mistake, because there's a heck of a lot of things that makes this very powerful. Okay, so if it was an invariant, you see, these guys are unit matrix, always. Okay, always unit matrix. These, rarely. In mechanics. In mechanics, almost everything you make is non-orthogonal. Okay, but that is the inverse of that. That's another thing that we needed to say. All right, let's put it to work. We've got the Lagrange equations. We've got the Lagrangian as an entity that we're claiming is more convenient to do things. I'm claiming it's more convenient for getting into Coriolis and circular centrifugal type stuff, because that involves going around a curve, going around a circle. So what I'm going to do here is take the Lagrangian that we're used to. It's only a function of velocity, but now we've got this thing as a function of position, and it'll be a position of whatever coordinates we use. And then we mean velocity is r dot, and then we mean r dot is covariant vector q dot m conjugate. And then there's a sum over n, okay, right there. Well, what does that become? This is a classic Lagrangian written in curvilinear coordinates. It's the metric and velocities using the r and the phi in our case here, but in general some curvilinear coordinate system, okay? And then presumably u is also a function of those curvilinear coordinates, but not the velocities, right? Not the velocities. That cannot be a function of velocities. This has got it all. Okay, and then there's m here. The m matrix, remember? That's going to be constant too. Okay? So very often we try to absorb the m into that. But you see, you also got a 1/2 here, you see. This is weird because general relativity starts with this over 4 dimensions, including time. So coordinates become, one of the coordinates is time. That's a different game than we're playing here. Here we're using dots to indicate total variation with respect to time. Okay, I'm going to make that point several times again in this course as we go along. But you should probably see that we already dependent. Now here is what we're dealing with, a metric coefficients. So once you've got your Jacobian, you've got these guys, and you just put them together to make 4 of those, and you're off to the races. This gives a polar GCC form, and as I've said many times already, it's really an OCC. Okay, it's just going to make a job a little easier. All we're going to have here is RR and phi. We're not going to have R phi or phi R, okay? R phi phi. That's cool, right? We're rapping it now. R phi phi, R phi phi. Okay, so our matrix is very diagonal and very simple. 1 in R squared, that's all we've got. But all this beautiful physics comes out of that immediately. That's what's so cool about this. That's what makes the French so cool. The French way of doing things is very neat. Now Hamilton, it's got its advantages, but neatness is not one of them. That's the Irish. We're talking Irish, okay? Different culture, okay? They do some really Hamiltonian. That's what you hear about in quantum mechanics. You don't hear about Lagrangian much unless you're doing particle physics and you have really high energies. There's a reason for that. And we'll see it later on. Okay. What I want, this is from the preceding, but what I want to do is get the momentum. The generalized momentum, the covariant momentum. Okay, P sub r. Okay? That's the partial derivative of L with respect to r dot. And I'm going to follow with the other screen since it is clearer. And so we can point things out over there when they don't show up too well on this side of the pond here. Well, this one is not surprising. I mean, we're talking about a metric coefficient of 1, so r, it's just a distance. Okay, it happens to be a radial distance. So this is radial momentum. Okay, it has the usual linear mv form, product of mass and velocity. Okay, so I won't have to say much more about that. But it's in the mix of things which is going to fill up this blank space here. So now I'm going to take Lagrange's first equation, that is the partial derivative of the Lagrangian with respect to the velocity. Velocity number 1, that's r. Velocity number 2, that's phi. But let's do them both, okay? And that's what we've defined as momentum by our geometry before this, okay? But now, if you didn't do that geometry, this is your first time really to say, I gotta take this seriously, this relationship. It gives me PR, big deal, I knew that, but I might not have remembered that G phi phi was r squared, and so this is really cool. G phi phi gives them a moment of inertia factor mr squared automatically. For the angular momentum, that's what this is. P sub phi is the covariant angular momentum associated with the coordinate phi. Phi angular momentum. Does that make sense? Okay, that's cool. Now we haven't used this guy yet. That comes right away. I've got to take derivatives of the Lagrangian here with respect to the actual coordinates, not the velocity. Okay? To do the other half of this work. Okay, so this is from the preceding page. Let's go for it. Here they are. This is P dot R. So this is telling you something about changing momentum in the radial direction. That's a generalized force. Okay, that's partial L with respect to R by this equation. Okay, which is second Lagrange equation. This is the first. Okay, so it's neat to separate things this way. Okay, so what I'm ending up here with is a partial derivative here of the L with respect to R, and the only place that I see an R here is right there. Remember, it's a partial derivative, not total. Okay, we get that later. But here I've got an R squared. Okay, so when I do a partial with respect to R, which is what I'm asking for here, I'm going to be going right to that one there, and immediately canceling a 2 with this one, I take the derivative of R squared to give mr phi dot squared. Oh, I think we've seen that before, haven't we? Remember mr omega squared? There it is. Mr phi dot squared. Phi dot is omega. right? Angular velocity, generalized velocity. Isn't it cool? Okay? So we got centrifugal force now. We picked up our moment of inertia, we picked up this. Okay, this one, okay, if I take a partial L with respect to phi, all I'm going to get, there's no phis anywhere here. There might be one there, right? If you had a potential that had some bumps going around, that's who would show up right away, the partial with respect to phi. With the minus sign, okay? But if this was only a function of r, which is usually the case because those are so easy to solve, you get lots of those later on, okay? Then this is 0. If it's not there, then I have nothing left but 0. So there's your conservation, okay? P phi is constant, that is conserved, if the potential has no explicit phi dependence. Okay? Well, that's cool. That's, you know, another law, you might say. Now, are we done? No, we're really not. Because what we have to do is take the time derivative of the things that we've got here to get at the second derivative, and we have a couple other things that are needed here. But let me bring this screen up to the point we are sitting at pretty much right now. The next thing that we need to do is written there, and that is we need to get P dot directly from the first Lagrange equation. So let's go ahead and do it on this side too. What we have here is the derivative with respect to time of this momentum expression here, which is the metric tensor summed over the velocities, radius velocity and the phi velocity here for a particular component m, and m can be either r or phi, so we've got a couple of things here to do. And then, once you get that, you equate it to whatever you got for P dot M, either this one or this one. Okay. So this is where we get the Coriolis effects, by making that move right here. So this is from the preceding page, and I might as well put this one ahead to that point too. So this is important right here. This is the real grindy work for much of the Lagrangian technology. Okay. So P dot R, that's dp dt, not partial. Okay, you see that pretty easily just from this equation right here. But what we got before was this one. Okay, so here we really are saying that the centrifugal, that center fleeing force, equals the total centripetal, that center pulling force, and that's this guy right here. Okay, here's your centrifugal fleeing. That's a fleeing force. It's positive R, and then whatever this comes out to be, it might be negative if the U was downhill. So we would just add to this by having this be positive then, but usually this say it's positive, so I subtract that. It would be something holding you, center pulling force due to whatever potential this thing happens to be holding in the radial direction. All right? So it's this maneuver, these maneuvers that make the actual equations that you would either solve by doing techniques of calculus and differential equations, or get on the computer and do a Runge-Kutta with these things. And we'll say more about that when we do Hamiltonians, because they do better Runge-Kuttas. Anyway, here's P dot phi. I take dp phi dt, that's this thing right here. But here, of course, is the actual phi that we have. In any case, when you do that, you have here a p phi equal to mr squared phi dot. And when you take the derivative of that, the time derivative of that, that's that thing right there, you get two terms there. You get, and now everything varies. No partials now. I'm doing total time derivatives, so I got to do a derivative of r, I got to do a derivative of phi dot. Every one of those things has to have a time derivative. So now I get, finally, generalized angular acceleration, that's torque, and the torque due to Coriolis. This is the angular acceleration due to the interaction of velocity radially with angular. That's phi dot right here. There's your omega. Okay. Now remember that angular momentum is conserved if u has no explicit phi, but you don't get rid of that. That's still there. That Coriolis thing is still going to be there, regardless of what u is. It's not dependent on u. That's kinetic. That's the Coriolis. So we got to talk about this, and we only have a few minutes to do it, but they're going to be a fun couple of minutes. So here are the equations with a mass in them. Okay. I can script that out. Okay, and basically with the potential not there, and what I'm talking about are hurricanes. Okay, but any weather system in either the upper northern hemisphere or in the southern. We're doing northern here. Okay, so we're taking these equations from that relationship and putting some hand waving on them. The angular acceleration is the one that's most interesting because that's what's driving the incredible velocities near the center of a hurricane. And you have to treat the signs carefully. What we've got is phi dot greater than 0. We're talking about the rotation of the Earth, okay? If you were at our latitude, okay, you're sort of on the side of an Earth that's going around like this. Goes around like this, sun comes up, right? Okay, so we're talking right-handed motion of the Earth, all right? And the result is going to be right-handed motion due to this Coriolis thing here. And check to see if that sign is right. But in any case, we're basically arguing about this -2 r dot phi dot, and then r's without a sign, okay, more or less constant, at least nearly constant. There will be an inward flow, okay, to preserve the low pressure. That is, if you have a low pressure, okay, it's dry. The air tends after a long while, it's maybe back effect, but starts to go in like that. But it just doesn't go in and collide and come bouncing back out again. What happens is it feels the Coriolis force. With phi dot greater than 0 and r dot, we're talking about r dot less than 0, so we get rid of the minus sign here, and that gives me a positive phi dot dot. Presto. Either tornado or hurricane in the extremes, or just a nice set of, little breezes that are going counterclockwise. That means in the northern hemisphere system, which, because of the rotation of the Earth, a much smaller effect is all of these things drift from west to east, so they all drift this way. So before the storm in the northern hemisphere, you feel warm, hot, muggy air. Extra muggy because of the Gulf of New Mexico is dragging some of that moisture up. Okay? When it's past, beautiful, clear, dry, cool air, right? This happens all the time during summer and winter here in Arkansas, right? So we have a very special rule here that I like to say is the deep quantum rule is flow tries to mimic the external rotation. It tries to get the least relative velocity of everything with everything, because that's the beat frequency. You're trying to get that in there, that's your energy. That's just trying to be low. But you can see the effect of this equation very clearly. Now what this is the famous skater, right? She or he pull arms in. If you got a little bit of velocity here, you pull them in and you speed up. Slow down by pulling them out. But if you got a low pressure area here that's pulling like mad. Now, of course, how that's built, that's another piece of physics. But anyway, let's our homage to this guy, this is Irma, okay, 185 miles per hour we're talking about. And we're talking about forces that go up as v squared. That's the energy, the momentum that eventually washes out. So at 100 miles an hour, if you've held your hand outside of a car going 100, right, it's really a lot, right? Go 200, it's 4 times that. If you've ever flown an airplane, try to stick your hand out of the vent window, you'll almost feel your finger being ripped off. This is happening continuously. 185 is a really fast airplane. I've never flown one that fast. 65 is about the fastest I get. Okay. Oh dear. Shut up. Okay, here's a hurricane to end all hurricanes. Cassini just went into this planet, Saturn. End of mission. What a mission, and this is really cool. This is an enormous hurricane at the pole, which has hexagonal symmetry. I don't know what the heck's happening there. How do we turn this thing off? Anyway, we're almost done anyway. This, as I say here, the lecture ends here, so maybe somebody knew that serendipitously. But this is an amazing piece of physics. I don't know what's going on there. There's people studying the data from that amazing spacecraft for probably 2 more generations. I mean, until we get to go there and look some more. Sure. And I don't see that in the budget right now. Okay.
We got Juno around Jupiter now.
That's true. Jupiter is also
Wild
weird.
orbits.
And it's got lots of hurricanes at middle latitudes. Saturn doesn't even show them. Yeah.
So is it due to some quantum mechanical effects that the geometry is exactly?
Well, I was being, you know, a little careless there, attributing the quantum effects. Probably what I should have showed is the mechanical effects of this gyroscope here. And when I turn it this way, it lines up with that thing. But when I turn it this way, see how it comes around and oscillates around the other direction? So it's behaving like a magnetic dipole in a magnetic field made by me turning it. Well, that's a quantum mechanical effect right there. That's this, derived from the spin equations. Precession of a spin vector around a Hamiltonian vector, which we will cover very much in Unit 4. So that's a case where quantum mechanical derivation of a force law is trivial. But the classical mechanic derivation is not trivial. So I always use the idea that what this thing wants to do is line itself up and go in the direction that you're going. It'll line, it wants to get its relative velocity to you low, as opposed to the upper state where it goes contra. That's an excited state. And there are cyclones that counter. But that's an excited state, and it doesn't last very long. When you make a counter tornado, it usually knots up and does something crazy, and maybe turns into a proper tornado, which goes in the northern hemisphere counterclockwise as opposed to clockwise. I don't know if that answers your question, but there's a lot more questions hiding behind that. Okay. Well, Thursdays for Hamilton, it's interesting in a mathematical sense. We won't have time to do too much of the cool things. That's the rest of the course. But the Hamilton should be known to you. You know, we're giving it full time here.